Okay, so for the second half of the tutorial, I will talk a little bit about graphical representation of causal effects. And so the modern theory of causal diagrams mainly arose within disciplines of computer science and artificial intelligence. These are some of the comprehensive books that you may want to read for, of course, a more in-depth discussion on this topic. So these causal diagrams are useful to classify sources of bias and to identify potential problems in study design and analysis. And as we will see, the graphical approach is intimately linked with the counterfactual approach that we just talked a little bit about earlier in the day. Right? So we can consider the diagram below with 3 different nodes and 3 different edges. And we will adopt the convention that time flows from left to right, so L is temporally prior to A and Y. This is a direct example of a directed acyclic graph. It is directed because all edges are arrows, and it is acyclic because there are no directed circles. All right, so here, so if this arrow happens to point this way, then we will have a cycle, directed cycle, right? But clearly this is not so, and we have a DAG diagram, right? A DAG diagram here. So notice that the standard causal diagram does not distinguish whether an arrow encodes harmful or protective effect. DAGs have many other applications besides causality. Here we only consider causal DAGs. We shall say that a graph is causal if common causes of any pair of variables in the graph are also in the graph. So the presence of an arrow, for example, from A to Y, indicates either a direct causal effect for at least one person, or we cannot assume such an individual causal effect do not exist. So the lack of an arrow, conversely, would mean that we know, or we can assume that there's no direct causal effect of A on Y for any individual in the population, if there's no arrow from A pointing to Y. So for example, here we have an observational study where L is a confounder of the effect of A on Y. Right? So here we assume that the treatment has a causal effect on the outcome, and then the confounder itself has a causal effect on both the treatment and the outcome. Okay? So here is an example of a randomized trial where A is randomized by independent coin flip, right? A random assignment. So in this case, prior to the treatment assignment, there's nothing that will be causing the treatment assignment because itself is just a randomized, right? So there's nothing that points to A in this causal DAG. So 2 variables are marginally statistically associated if one causes the other or if they share common causes. Otherwise, they will be marginally independent. So for example, the randomized trial causal DAG, A has a causal effect on the outcome Y, implies that A and Y are statistically associated, right? So there's this path from A to Y, and it's a causal path. So a path between 2 variables in a DAG is a route that connects the 2 variables by following a sequence of non-intersecting edges. And we will see some examples on this. A path is causal if it consists entirely of edges with their arrows pointing in the same direction. Otherwise, it is non-causal. So suppose A represents carrying a cigarette lighter, Y is lung cancer, and L is indicator of smoking status. So if let's say a person smokes, then it will cause him to carry the lighter, right, more often, and also it might have a causal effect on the lung cancer. So an analysis that ignores L will conclude that A and Y are statistically dependent, even though not causally related. This is because of a common cause L, and therefore this path is non-causal. So assume that there is the absence of this arrow here, this direct causal path. Then there's another open path from A to Y through L, right? Such that A and Y will be statistically dependent. So another example, A is now a gene that has a null effect on smoking status, and smoking status has a causal effect on heart disease, L, which is also affected by A. Okay. So here we have an example of a collider, right? So the only path linking A and Y is through this collider L, right? Which is a node where two arrows intersect. So here A and Y are said to be marginally independent because at this collider L, it sort of blocks the path from A to Y. Right? So this is in contrast to this type of path where these two arrows point to A and Y from L. This is the open path. So notice here the two arrows intersect at L, pointing into L, and this is a collider. Right? So when there's a collider, the path is blocked. So suppose A is aspirin, Y is heart attack, and B is the mediator of the effect of A on Y. So the following graph assumes that all of the effect of A on Y is through B. So conditioning on B blocks the path between A and Y and makes them conditionally independent. So it blocks this path. The box around B is a graphical depiction of looking at subset of individuals with the same value of B. So we only consider individuals with the same value of B, i.e. analysis is conditioning on a certain value of the variable B. Okay. So conditioning on the common cause L of A and Y blocks the path. So notice that this path used to be open. Right? So if we condition on L, it will block this so-called backdoor path from A to Y. Right? So that if A indeed has no causal effect on Y, then A and Y will be conditionally independent. So this is the justification for stratification on confounder to adjust for confounder. So it's sort of using the graphical approach, we see that conditional on L, it blocks this path between A and Y. So let's revisit the genetic example. So notice here is a collider, and if we condition on this collider, it actually opens up a path between A and Y, right? By conditioning on the collider here. So that although A and Y are marginally independent when we do not condition on L, they are now conditionally dependent once we consider a given value of L. This is known as the collider selection bias. So to see why, suppose an investigator wishes to build a predictive model for smoking status. So knowing that a patient with heart disease does not have the gene provides information about smoking status, because in the absence of A, it is more likely another cause of L, such as Y, is present. So for example, if we know a person has lung cancer, then if he did not have this, let's say this gene is harmful, if he did not have this gene, then it's more likely that he smokes, right? Because both of these contributes to the development of the heart disease, right? So conditioning on a person with heart disease, we can see that the gene and the smoking status will be associated. So this is intuitively why we have them A and Y conditionally dependent once we condition on this collider L. So two causes of a given effect generally become associated once we stratify on the common effect. Okay, suppose the previous deck is extended as follows. So here is exactly the same as the previous deck, but here L causes another variable C here. For example, C can be selection into a case control study depending on the outcome L. All right? So graph theory tells us that conditioning on a variable C affected by a collider L also opens up the path. So you don't have to condition on L itself, but if you condition on a variable C that's affected by L, it will also open up this path between A to Y. So notice that if we do not condition on C or L, then this path will be blocked because it's a collider. It's a collider here. But once we condition either L or C, this path will be open. Right? So this means that sometimes conditioning is you must be very careful to condition on certain post-treatment variables, right? Because it is not necessarily the case that the more variables you condition on, the more valid your inference is for the causal effect, because you might unintentionally condition on certain variables such that it opens up another path between your treatment and the outcome. So now we will talk about deseparation. So a path is said to be blocked if and only if it contains a non-collider that has been conditioned on, or it contains a collider that has not been conditioned on and has no descendants that have been conditioned on. So this is just a summary of what we talked about for some of the examples earlier. So two variables are said to be deseparated if all paths between them are blocked. Otherwise, they are said to be deconnected. So two sets of variables are said to be deseparated if each variable in the first set is deseparated from every variable in the second set. Okay? So this is just a definition of deseparation to sets of variables. So for example, here, A and L are not marginally deseparated because there's one open path, right? So this is L and A are not deseparated because there's this arrow here, right? So this collider path is blocked, right? This is a collider here. In the second example, A and Y are marginally deseparated because the only path between them is blocked by the collider. So this is the collider here. This is the only path, and it's blocked. So as we talked about, if we condition on L, then this path will be open again. And the A and Y will be deconnected in that case. So deseparation, A is conditionally deseparated from Y given B. So condition on B blocks this path, and therefore we say A and Y will be conditionally deseparated, given B. The second example, here is a collider, but once you condition on L, it will open up this path. So we say that A is conditionally deconnected with Y given L. Right? And this last example, again, we see that if you condition on a descendant of L, right, you will also be opening up this path through the collider. So A is conditionally deconnected with Y given C once we condition on C. These are just some examples of deseparation or deconnection. So confounding bias arises when the treatment and outcome in view share a common cause. So notice that the here, right, the treatment and the outcome, there's a causal path through this arrow, but there's another open path through the variable L here. And this is called a backdoor path, right? So this is a backdoor path. So this is a direct causal path, but there's a backdoor path here. So even though it is the case that A is not causally related to Y, so even when this arrow is absent, right, A and Y will still be marginally deconnected due to the backdoor path through L. And so we see that A and Y will still be marginally associated in the data. So notice that if we condition on L, right, this confounded L as we usually do in our analysis, then it will block this backdoor path, right? Such that if, in addition, this arrow is not there and this path is blocked, the A and Y will no longer be associated statistically, right? So this is the reason why we usually condition on the variables that we think are confounding on the effect of treatment on the outcome. So randomization eliminates all backdoor paths by cutting the association between A and L. Right? So if A is randomized, then we do not think that there are any variables that will cause A, right? Because itself is just random. It's randomized by, for example, a coin flip. So we will not expect to have any backdoor path connecting A and Y in that case. So more generally, in the absence of randomization, the backdoor criteria states that the treatment effect is identified if one has observed enough variables to block all backdoor paths. That is, if the treatment and the outcome are deseparated given the measured covariance in a graph in which the arrow out of the treatment are removed. Okay? So, for example, in this case, if we do not consider this causal path coming out from the treatment, right? And we look at all other possible paths from A to Y, right? Then if we block this, if we condition on L, it will block the only path, remaining path from A to Y. So if we condition on L, we can attempt to identify the causal effect. Right? So this is so the backdoor criteria basically states that you can identify the treatment effect if you have observed enough variables to block all the possible backdoor paths. Okay? So i.e., we want the treatment and outcome to be deseparated given this measured covariance in a graph in which the arrow out of the treatment are removed. Okay? So this provides a graphical way for us to identify which are these so-called confounders that we should condition on, so that by conditioning on this set of covariates, we can block all backdoor paths from the treatment to the outcome. Okay? So instead of, so this is a very intuitive way for us to really, before any analysis, we can write down we can draw a deck and see what are the relationships. And of course, these are very simple examples involving 2 or 3 variables. But in actual studies, you might have tens, if not hundreds of variables. And in that case, a graphical approach will be very useful for us to identify the ones that will allow us to satisfy the backdoor criteria. So these criteria answer 3 questions. Does confounding exist? Right? If there's an open backdoor path, then confounding will be there. Can confounding be eliminated? So we need to identify all the variables that block the backdoor path between the treatment and the outcome. And if some of these variables are not measured in your study, then it is possible that we can never eliminate confounding. And 3, what variables are necessary to eliminate the confounding? Well, we can identify those variables, but whether they are recorded in the study will be another challenge, right? But this graphical approach allows us to actually identify in a very systematic way the variables that we need to control, right? To elucidate the causal mechanism. So crucially, it can be used to decide whether one has measured a sufficient set of confounders to block all backdoor paths and therefore to adjust for confounding, right? Using this graphical approach. And also we have to be careful not to condition on colliders, right? Because in that case, it will open up another path from the treatment to the outcome. And so it is not the case that we should condition on as rich possible a set of covariates in the study, right? We need to have an understanding of the causal relationship between the variables before we condition on any of them. Okay, so actually this will be the last few slides for the tutorial today, and I think I'm ending quite early. So we have, of course, early in the day, we talked about the no unmeasured confounding assumption using the counterfactuals or potential outcome language, right? So still fresh in everyone's mind, we have the treatment is independent of the potential outcome given a set of covariates. In randomized trials, of course, we know what these covariates are. In observational studies, we make the assumption that essentially conditioning on these covariates, we have sort of a randomized study by nature. And also we talk about the graphical approach, how to, the condition for identification of the causal effect. That is, if we condition on a set of variables that blocks all backdoor paths, that L is sufficient to adjust for confounding. Okay? So this is the graphical way of looking at it. But we see that in the graph, there are no potential outcome language in the deck diagrams. So how do we unify these two definitions? Because when we look at this no unmeasured confounding assumption, there's no graph. And when we look at the graph, there are no potential outcome symbols in it. Okay. So Richardson and Robbins introduced the single-word intervention graphs to unify counterfactual and graphical approaches by explicitly including the counterfactual variables on the graph. So the swig depicts the variables and causal relations that would be observed in a hypothetical world in which all subjects receive treatment A, level A. So we will look at a very simple example on the single word intervention graph. For a detailed understanding of this tool, you should refer to this reference here. So this is the original causal deck diagram. Okay. So we see that if we do not consider this arrow that comes directly out from the treatment, there's actually one open path here, the backdoor path, right, through U. So U goes to A and then U goes to Y. Okay, so by the graphical approach, there is by the backdoor criteria, right? We need to adjust for this confounder U. However, it is also the case that if we condition on L, then this backdoor path will be blocked, right? Because the U arrow going to Y and there's a U arrow going to A, but if we condition on L, it will block this path. So this backdoor path will be blocked, right? And in terms of the potential outcome language, we say that conditional on L, right, we have the exchangeability assumption. Right? Conditional on L, we have the exchangeability assumption. So how do we go from the causal deck to the potential outcome language? So how do we unify these two? So we can think of the swig as intervening on the treatment variable. So this is the same for everyone in the population, little a, right? And because this is the same, there's no arrow going into this node, right? So these two parts will be separated. And because this arrow points to Y, and now we are setting A to be equal for everyone in this world, then this will be actually the potential outcome for treatment set to A. And we can read off the conditional exchangeability assumption from this swig, right? So how do we look at it? So notice the A and this Y of little a, there's a backdoor path, right? Again, there's a backdoor path. But if you condition on L, then this backdoor path will be blocked. So therefore, condition on L, the potential outcome is independent of A, right? So by doing this, by this swig construction from the original causal deck diagram, we can actually read off the exchangeability conditions using the potential outcome language. So of course, this is a very simple example that we can sort of immediately write down without even constructing a swig. But imagine more complicated scenarios, the swig will be very useful in those situations. Okay. So in today's tutorial, I talk about, at a very basic level, some introduction to the definition of causal effects, some very basic statistical methods. By basic, I mean the examples I consider are very basic settings involving just point exposure, right, and a single outcome in both randomized experiments as well as observational studies. Following my tutorial, there will be another tutorial by Jonathan, who will be talking about much more complex settings involving longitudinal studies, whereby your treatment and your outcome can both be time varying. We also talked about the graphical representation of causal relationships. And finally, we talk a little bit about tools that can allow us to unify these two ways of understanding causal mechanisms. Okay. So I hope this tutorial merely serves as a way to inspire interest, and you are welcome to read more on these topics. And I think the slides will be made available through the Institute for Mathematical Studies, Mathematical Sciences, and the references are also appended here. So these are some of the very highly, also they are very highly cited in causal inference, and they will provide a good read. Okay, thank you very much for coming. Yeah, thank you.